aluminium alloys can cause shrinkages. You know, from liquidus to solidus is the freezing range. When the freezing range is long, say 100 degrees for LM4 and about 75 degrees for LM25, these castings will not solidify immediately. They stand as liquid for a very long time and keep the gas. Another one is short freezing range alloys, which are more prone for shrinkage. For example, LM6, LM9 and all having hardly about 30-degree freezing temperatures. When these castings are produced in these alloys, they are much prone for shrinkages because there is no range of the temperatures. These alloys are LM6 is more suitable for PTC castings where you are required to cool the casting very quickly. However, LM6 is very versatile. It can be cast by gravity, sand casting, and the high pressure die casting. So one factor which affects shrinkage is solidification range. This is what I am talking about. This is the range we are working. This is how you calculate the freezing range. This is aluminum 100%, the silicon 0%. It goes up to 10, 11, 12 is common. See, this is the LM4. LM4 is quite long, son. 700 minus 600. This is all these are solid, all above the liquid and liquid plus solid. Another way is the shrinkage during solidification. When this, as I said, that it is due to the volume contraction and the pure aluminum shrinks at 6.6%. The other aluminum alloys, the range is varying from 3.5 to 8.5%. One more thing is that gas evolution. Gas bubbles are high pressure regions in the metal, and the shrinkages are low pressure regions. If both occur at the same point and come spot, the shape is slightly different. Sorry, leakage. The shape is like a dented circle, see, like this. This is called the linkage. This is a new terminology which I wanted people. Another reason this one is cooling temperature is very high. It is also going to aid shrinkage effect. If the metal is superheated for a very high temperatures, more than 760, there is likelihood of shrinkages. Rate of pouring also gives rise to some shrinkage. If the rate of pouring is very slow, the metal enters the cavity also at a lower temperature, shrinkage defect can occur. For thicker castings, it is advised to pour as slow as possible. Impurities in the aluminum alloy also can nucleate shrinkages like aluminum oxide. If the calcium content is more than 0.015%, it can also cause micro shrinkages. So, also, if the riser size is very less, also shrinkage can occur because of the lack of feeding. Riser should solidify after the casting has solidified. It should not solidify earlier than the casting. These are all the various circumstances where you are getting shrinkages. There is one area, this point is called theoretic point, where the silicon percentage is 12.6%. Around this range, but some others say it is 11.6, whatever it is there. At this point, aluminum alloy is solidify like a pure metal. There is no range, so it gives rise to filling. All the points solidify at the same time. That is the drawback. So it is better to avoid this 11.6 to 12.1 percentage in any alloy. Now, die condition also important. Say when the die is poured, the heating is really important. If the low shrinkage, if the initial temperature is low, it can also give rise to this one. Conductivity also can cause. If the die can conduct very good, if faster, shrinkages will be very much less. If too slow also, shrinkage can occur. Die shape is also important. If the die cavity has got a lot of sharp corners like this, it can also give shrinkages, and also if you are having a knife edge like this, it can also cause hard shrinkages. It is better to have a shape like this. One way to prevent shrinkages at the casting design stage itself, if we can talk to the customer and request him to reduce section thicknesses without affecting the product function, it is good. It is not favorable to aluminium casting to have very high thicknesses because very high thicknesses should be very late. Central line shrinkage, there are 4 or 5 methods are there to solve and reduce shrinkage cavities. Provide sufficient riser volume and ensure it connects most of the die cavity portion. This is one of the major problems we encounter in any die design. Avoid necking, that is when the riser connects the casting, there is no sufficient material means the feeding won't come through. This particular one, avoid necking, is one of the major constraints I have seen in many die casting problems. Increase thermal conductivity, that is chilling, nothing but chilling. Remove the die coating on the die spots because normally grab dies are coated with the refractive coating, and those coatings can be removed at spots where you are having sections. It can also give some solution to solve the shrinkage problems. Air cooling also can solve some shrinkages, and the copper chips also can conduct the heat very fast from the casting and make it solidify faster, and shrinkages can be reduced on solid load. Reduce certain thicknesses in the shrinkage areas. All these 4 or 5 methods are there. We will apply all these or a few of this one and try to solve. I will demonstrate the ability now in some case studies. Now I tell you, air cooling. This is the centered air flux through which air is supplied. This is the die cavity. Here comes the mass. So that this portion of the die will be always very cool, and this will help to solve the problems. This is the centered air flux having a hole of 0.5 mm diameter. Metal will not enter this. Unfortunately, nobody is making this blood plus in India. All these blood plus are getting imported from Japan only. They supply millions of these inserts blood plus to all over the world. Another method is to provide copper chilling. This is the casting. This is a very big boss. Having shrinkages means it should be hunted with a copper chill, and this should have a head, and this head must come to atmosphere. If you are going to put a blind chill, it will not be effective. It will give more shrinkage by overheating. This chill should be cooled by his one head, and this place, even he can spray some air also on this one. So all the shrinkages can go because this solidifies 5 times faster than the steel. Sometimes it is possible to provide hatch marks of 5 to 5 mm. This can also give some cooling effect and solve many shrinkage problems. There are some techniques on that. The size can be 5 mm into 5 mm diamonds. Now I am going to take up some case studies which may have some interest to you. This is one casting. This is called a cylinder. It's weighing about 3.6 kilograms. Very, very critical casting. The name is cylinder, and the aluminium alloy is LM4, metal weight 3.6 kilograms, short weight is 6.9 kilograms. It is made by static gravity, and all the diameter is made of ENA steel. Very, very critical casting. Not even one small knot of shrinkage is allowed, or any void is allowed in the main bore. This is was used once in the air brake castings for cars. I'm sorry, these commercial vehicles. And these should not leak at a pressure of 12 bars, such a high pressure, and the finish requirements are very, very high in the board. Okay, what is the problem faced in the casting? This is the problem. In this part of while air pressure testing, some fine leakage was happening. This also, this is part. If you take a section and see, you get a very, very fine linkages. So how to solve this linkage problem? Studies made and investigations. This is the full short view of the casting. From here to here, this is the casting. There are three big rises, 1, 2, 3, 1, and this is the say, controlled way of pouring. 1, 4, 2 cross sectional area. It's a beautiful system. It works. But in this area only we are having shrinkage. Why it is so? We take a section and study this one. If we take a section and study this one, what I'm saying, being this wall thickness is only 4 mm. So the feeding is not coming from the main racer to this area because this has already solidified this one. This is called necking, what I told in the few slides back. Here, this is such a big riser, even not required. So this necking has made no feeding at all coming to this area. So what's the pathetic? Only 4 mm. We requested the customer to make it about 8 mm. He said no, we cannot make it so big. Then see this R shape. How do you say it is shrinkage? When you take the section and then polish and white, the shape is R-shaped voice notice. So it is confirmed as shrinkages. So how to solve this problem? The only way is we are left with this cooling methods. When there is no feeding possible, you try to find all sorts of cooling methods. This is one. So how to cool this one? We have to find some method. This is a solid, I mean, it's a bottom core. Is from this one. Also, the core is getting overheated. Since the metal is poured from the top system, it comes over there and the metal falls readily on the core. This is a hollow core, and this section is getting overheated. Additionally, on top of there no feeding, at the same time, it is giving shrinkage problem. So, how to cool this area? So, as a attempt, we requested him. We found the thickness 15 mm here. This thickness in this area where the shrinkage is predominantly occurring. So then we made a request to the customer whether it is possible to reduce some material in this boss area. Yes, agreed and then made about 5 mm reduction and the section thickness came down to 10 mm. From 15 to 10 mm. It was also some aid to reduce it. But he did not solve the problem. What to do? Therefore, the next option is left to us to cool the shrinkage areas further. How to cool it? This casting is made. This bore is formed by a core which is hollow. So we try to put some copper chills with the taper things and try to cool it and try to supply air. This is the one and the shrinkage was eliminated, but the solution was not agreed upon because the cooling air started leaking through these copper chills holes. After some time, after a month, we see all small air leakages started coming out. Also, the shop is not very happy about it because it's very noisy. In such an about 3-4 minutes of air flowing through a 150 diameter core, we made a very noisy the shop floor and also the shop floor become to the moisture and the oil present in the compressed air. Totally workers did not like it, although the problem was sorted out. So we have to find a new solution. Then we thought the hollow core does not conduct heat as efficiency as a solid core which has got continuity. So we wanted to try one solid core, 150 dia. We made one solid core like this. No copper chills, no this thing is there, so no air is required. To our surprise, all the shrinkages, this core conducts faster than a hollow core with all this. So in this core, there is no copper chill, no air required. Problem was totally solved. There was a big saving in the air compressor, and the shop became very much less mass. And the problem was shrinking was totally solved. So here what we have learned is try to reduce the section thickness as far as possible. Try copper sheet with the cooling and the fixed simple drain plugs and the pass gap. This is the one way. The casting name is inlet manifold for cast. There's also that. There are many problems and we took only one problem. This is the aluminum casting. Wherein the air and fuel are getting mixed. This is the mixing chamber. It's all the ports. Here comes the air and also this fuel is separated somewhere here. All that one. Alloy is AC4B. The casting weight is 3.61. The total casting weight. And the casting weight actually goes to 7 kilograms. This one of someone. And the general wall thickness is only 3.5 mm. This is produced using tilting gravity casting. What was the problem faced? This is a gauge port. This is a port wherein you fix a drill and tap and put the tap here. Here they put the gauge and this is the mounting holes. And like that. These are tapped holes. And in this hole, after when the casting is checked in the pressure test, they have started leaking in this. All the air leak is like that. And at the back side of this one, you find a mass like this. And this mass area, you are drilling a hole at the bottom. Here also you are drilling the hole. Here there is no mass. There are two holes being tapped. Only one is having a mass. Here not much of leak, but here only you are having leak. See the shrinkage. The whole area is so soft and then fully spongy also. We could see outside a lot of shrinkage. So how to solve the problem? Very difficult because this is totally inside the area. So this is fully like this one, box like this, full of palmed sand. Very difficult area to access. So this is the main pressure. From here to here, there is no connectivity at all. See, you have seen when you provide a riser, you should have access to all the cavity portions. Here there is no way this feeding can come here. Also, this is hardly about 3.5 mm. All of ports are there. Though impossible to get feeding from here. Also, here is one mass away from this one. Here is also another one. So this area is a feederless region. But still there is a leaking. And this portion is formed a very complicated set of pores. This is formed by port pores. Now we will see this is the die which is mounted on the machine and this is the pouring way. Now wherein you pour the material and the whole die is tilted back. This is how the casting is. This is the core box to make this. I am just giving you the background of the process. See how it is. Taking the special phase. This is the core box. This is one half of the core box wherein the fourth one is located here and then on this. Now I'll show you how the casting is poured and then filled. This is the die cavity. This is the sand course. This is this one. I'll show you how the metal is getting filled. This is the metal bowl. The whole thing will tilt back slowly. See, this is the bowl. This is the metal filling direction. This is the sand. Very slowly. The tilt time is 12 seconds. After which 4 seconds will be very, very slow filling time. Okay, it fills and then now the die is vertical and the machine is horizontal. This is the horizontal. Those who know about the now the metal is filled. In the tilting gravity, the runner and the riser both are same. So there is no need to have a separate one. This itself acting as a runner as well as riser. But this portion is totally away from the main riser. There is no way to do it. This is one casting. This is another casting. This is a 2-in-1 casting. You see, and this mass is formed at the bottommost point of this casting. There is no way to get any feeding to this casting. All are fully sand cores. Very complicated one. I'll show you how the leak occurs. When the gases were made and produced and subsystems were made and moved to pressure testing, this is how the air, like that air goes down. We made the following investigation to sort out. This is the section B of the gas. This is the bunk, which is porous. Through this only, all the air comes and here not much, but here only a lot of problems. See the shrinkage burst. The section of this area is going to take a section. Totally shrink, very, very micro shrinkage areas. And this area is totally formed by a sand core. And it's a very bad conductor of heat. It remains very, very hot. And this portion is fed by this portion. So this portion is like a small riser feeding this area. See how difficult area we have got. This is the shrinkages. Also, the polished section indicates shrinkages as well as gas blowholes. How do you differentiate a gas blowhole and the air blowhole? Mean gas blowholes are round in shape like air blowholes, but the surface will be very shiny like aluminium. You can see like a pure aluminium silver color. Air blowholes are same color, same shape, but the bottom is grayish because of the air. It contains oxygen, so the bottom will be rough. So there are two problems now we have to solve in the past. One is the shrinkage in the past and the resin gas blowhole, because these cores are made out of shells and glasses. We will take one by one. We made one caution effect diagram as per the Ishikawa. We made that one. And from that diagram, we made a matrix diagram applying YY and how analysis. It took us nearly a week to do this one. It's a very big diagram like this. I make it simplify it and show you. This is a very, very powerful diagram. This is about the section. Curve section, the shape is odd, so it is called this. And also some holes are round shaped and the bottom was grayish, and some shape with brightly polished. And some pinholes were also seen due to either gas. So in that box, there are 4 defects are there. But the most significant item is interdendritic shrinkage and also the round shape with the polish. Resin gas blowholes are more than the air blowholes, not much. This is a very, very small level of. So how to do that one? Shrinkage, air blowholes, resin blowholes, and pinholes. This shrinkage is due to lack of feeding, which is not known to us. Air blowholes are much in this because the process is doing by tilting level die casting, so we did not find much air blowholes. But this is there because there are 2 big sand cores made out of resin coated shell sands. This was eliminated almost by effective degassing. Lack of feeding in the past. Why? Away from the main place. How to do them? Try to provide feeder. So we tried to provide a local feeder and it was a failure. I'll show you how it is. We explore the possibility for reducing the bar size. Because the customer and he said no. So it's not possible because of the other reasons. And try to cool the bars area in the sample. This is the only option to sort out. So we started our action plan from this. I'll show you one by one. This is the sand core. We thought of providing a feeder, a kind of a blind based here, but practically it is impossible to make a core as suggested by our matrix diagram. The solution was not practicable, so we left it. Second one is we try to ask the customer whether we can reduce the size, so not allowed at all. We cannot reduce even one number. Okay, fine. Then we try to put some sintered vent plugs, the bottom one, and try to apply air in this one to cool the boss area. Shrinkage has come down, but not fully stopped. Still we are this. Then we try to apply some aluminium paint. Apply aluminium paint on the boss area, forming one, and try to pour some casting. But the shrinkage has reduced, but not acceptable level. But some gas holes has come due to the aluminium painting. So the solution was not valid. Then we try to hollow the core where it is possible to do it. Because while core shooting, we could not do that because this is a one core pin is there. So the hollowing the core also is not possible. So we are fixed in all the corners. Now, how to do it? Air venting failed, hollowing failed, cooling air painting failed. So to find a solution, somehow using a YY and how analysis. This is the YY and how analysis. Why the boss is not cooling faster? Unlike the metal surface die, the boss is formed. The boss is formed by the sand core. So sand is a bad conductor of heat. So how to improve the heat conductivity? Remove sand. Try to embed a steel chill in the sand core to form the boss. This is the idea which gave us a lot of improvement. The new idea came. How make the conductivity more? Replace the conductive surface. Try to embed a steel one which will be faster, and the chill has got to be embedded in the rotating shell core machines. It's a very complex question. Also, the shell core is made with a rotating shell core shooting machine. Very, very difficult. Somehow we made it up. We make some tolerances for getting the pin. I'll show you that one. This is a very small pin wherein we have to stuck that particular chill. This is the chill made out of steel, and we made these tolerances such a way it will not fall down while we are taking the shooting the core. This is the one. This is the locating pin. This is a very tolerance is very, very critical, and we have made some types and found 0.1, 0.15 is working. It won't fall down much. We made some cores with the chill. This is the steel chill, this is the sand core, and we have put that. This is the shape of that particular. The badge was made and found no leakage at all. Everybody was happy, but the process very hard. To make a 1,000 numbers of this steel one is very, very expensive, and the solution was not acceptable to management. We cannot make 1,000 chills when we are going to supply about 10,000 gases per month. Where we make 1,000 chills? Impossible. So we have to make some other material for the chill, and also it should be cheaper. And we had a meeting among ourselves and why not we make the chill in a different form? Instead of a cap like thing, we made a chill form like that. With the button view and with the hole. This was made in a very interesting way. The same shell core itself made as a pattern, and we made a aluminium block itself as a die. That itself a different project. No time to explain that one. We made this chill in a very, very cheapest way and produced. And the chill was embedded in the core when it was shoot in the machine. Very good process, very interesting process. Afterwards, we do the chill. This is the chill, sand core. And the sand core came out like this. The chill, aluminium chill, and this is the sand. We made some. Also, we put this air cooling in the die. Steel chill, air cooling, Cinder plus. Such a care was taken. A few batches was made, no leakage at all. The mass is so clean and neat. Every shrinkage has been submitted because aluminium chill being a good conductor of heat, we are able to take out also. Here also this is one hole, this is a flat one. Everything was okay. It has taken us nearly about 3 months, 3 to 10 months to do this one. The problem was ultimately solved. So the lesson is this one. The question why and convert the root cause approach. The tree diagram was helpful to find some new ideas. The question how and how ideas for finding the new method of implementation. Everybody has sharp participated in this. The end of this presentation. This is one other casting which is very critical. This is called the wall body. I am not able to show the actual casting due to some reasons. I am showing the 3D picture of the machined sample to show the actual casting. Please forgive me. This is the machined casting of the wall body. Very, very critical casting. Petrol casting weight is 0.75 kg and the short weight is 1.69 kg. Application is very critical. It's a very safety critical component. What was the problem reported? This is one bore. This is some ball bore something. 80 meter, 80 diameter. And once it is machined, full of blowers, full of voids. One other area, this wall sheet area, lot of shrinkage blowers are produced. 100% correct. The die was made about a year back, and no casting will be supplied. They was asked to miss with the problem. Given a very good opportunity, I made some observations and investigations how to solve this problem. This is the as-cast drawing. All the we machined this blocked, all the holes are blocked. You see the casting as-cast view. But here you see this area has been excavated. Okay, this is the casting by which they make the casting. This is the shape of the casting. Came out of the die with a lot of problem. This casting only gave a lot of problem at the machine. Casting shape, this is the wall sheet, very, very critical. This is the 80 dia. This is a mass which was not cold at all. This was not cold at all. This is also like that. And a lot of material has been removed here and here and here. This was the casting shape I saw. This is the one I don't have the earlier one, so I am showing this one just to show. I couldn't get the photo of that one. This is a very big eraser on the over the H dia one. And this is the was. This is the earlier one. This is after modification. This is a big board on this one. Now, photo well. Now, what is the action taken? Cut sections were taken and studied. This is a very big eraser over the H dia board. This is a big eraser. But still you are having problem in this board. Why? It was a surprise to everybody. Such a big eraser was there, but still you are having a problem. And how do you say it's shrinkage? We took sections and saw all these things. The shape is odd. Odd shape means shrinkage. So it is confirmed it's a shrinkage. Now let us consider this casting as a two-in-one casting for the purpose of defect analysis. It will be very interesting. This is one casting. This is another casting. This area is a feederless area. This region is feeding is there but not effective. This is still there. There is no feeder possible because this is the main tracer. It has no connection to this area. But see this spots. Why is it guys? It was a surprise to everybody is saying. And I studied the casting once again. Why there is a problem? There is a necking is there. There is a big eraser is there, but the flow is not coming to the why? See, whole area to a depth of about 4-5 mm is material is removed from this to save material. See this one. Also like that on the other two sides, all the four sides you are having no material from the riser to casting. So this is hardly about 3 mm. This area if you take a section on through this one. So this is also like that. And also this is a heavy core area. This riser is so big, but the feeding is not coming down. See, this area big, but since there is lot of material removed, this because the neck is a constraint to snap. So what I asked him, is it possible to fill up all this one at least by about 3 to 4 mm? He said, okay. And also to provide core here, like this. Provide core on all these things and fill up these sections. If you do it one, also a pad like this one. If the section thickness is heavy, without any difference, fill up. The feeding will be much better. They have agreed and this change was made like this. Coring over all this one, filling up over all this. Also, material is added to this. This is like this. Coring and this is added. Full short the result was very good. The top riser became very effective and started feeding the gas very well. There is no shrinkage in the H-dia board. Now I am coming to the casting part. No shrinkage on the wall seat area. Why shrinkage on the wall seat area? The reason is very clear. It is isolated from the main tracer over the H-dia board. If you are saying, there is no way for the feeding adjust to the area of the wall seat. Also, the section thickness on the wall seat area is little high. More machining allowance was there. I saw that one, like this. See, this riser has got no connection at all. It stops there. Then there's no feeding can come over here. So, shrinkage is quite likely to happen. So, we have got left with only two options. Cool this one, and also, if possible, reduce the machining allowances. We found that the machining allowance at the bottom is 8 mm, the sizes. I said, you require only 4 mm. Why do you want 8 mm? You can have at least 1 or 2 mm less. The size was mm after machining. So, he asked them, they reduce the wall thickness from 8 mm to 6 mm or 5.5 mm. Only 1 mm, 1.5 mm allowance was given. It's a good thing here in this area. We made some castings with this one and found some shrinkage is gone, but the quality did not accept it. Shrinkage has come down, but the level is not to our quality requirements. What is next? We are in the fix. It was decided to go for a cooling methods on the wall seat area. It's of course no other area. And this wall seat area is formed, one bit of wall seat area is formed. Of course, there is a small border. So what we did is, we asked the operators to air cool it by nozzle, open nozzle, and also to cool it by a rag. They are close soaked by the dicoat dressings. I've got to apply it is gloves over there, and then pull it. But the result was good, almost okay, but the operators did not accept. They found difficult to work. They started selling, they started murmuring, we don't like to work in a hot day of 300 degrees centigrade with this, leaving our hand here and trying to cool it for 6-7 seconds, and then again to cool it by water and all is troublesome. So we got to leave this solution and find some other solution for it. It was decided to eliminate the manual cooling and try copper chill cooling. This was the decision taken by us. Then we provided a big copper chill over the core. See, the entire thing was made of a copper. This is only a small area, but this was replaced this by a big copper. Only face is farming. This area at all not farming at all. And the head is open to atmosphere. With this new top core, no cooling was required manually. See, and castings were produced and machined. No shrinkage at all in the wall scene. Everybody is very happy at the end of the case study. I am going to the fourth one. Ear blowers are on the just below the subsurface. This ear blow hole was opened after sound blast. This Ascast area, this is the ear blow hole. Very, very fine looking area. You can see upside down. This blow hole was seen after machining. It's a subsurface blow hole. Just to show. Why air blowers are due to air entrapment? Air blowers are always due to air entrapment while pouring. Lack of venting by design of the die, blocked air vents, no air venting in places, improper runner design, problems in manual pouring because some operator lifts the ladle about 6 inches and pour. So the metal carries air also from the atmosphere. I have seen many conditions. And turbulence will be pouring. The speed is very high at the ingate due to the height of the metal pouring. Also, vortex formation due to the improper design of the pouring base. There are the many reasons. So the causes for air blowers. Let us see how it comes. This is one very, very critical casting called cylinder casting. Alloy is LM25. Casting weight is 0.5 and this is the weight 0.95. Very, very critical. Even a very dot porosity is not allowed in the. This bore is limited to 25 mm dimension. High status universe. The static gravity was already with two cavities about a year ago before my involvement. No casting production, no good casting, not able to put the production. This is the problem noticed. After machining is bore, very big blowholes, 4 to 5 mm size, only 1 or 2 player size. Not many blowholes are not there, only one in many of the castings. And sometimes there will be 2 blowholes. Size will be able to 4 to 5 mm. That is the condition. No casting was produced, supplied at all. As I said earlier, why this is air hole? There is no sand core at all. So it is can only air, not this one. And the appearance is like grayish appearance and a full circle. So it is definitely air only. Now this is the current. It's a 2 cavity die with the pouring is done through this one. And this is one engage, this is one turn the bottom, this is also metal pouring area, this is also one, this is one. Lead is. So metal enters on all the reports. Fantastic. But this is not the right practice in now. This is how it's being put. After the post very nicely and comes down over here. Metal enters here, shifts. We don't know where the mistake. I saw the operation, there is no bad practices from the operator side. It's very then I wanted to why there is only 1 or 2 blowers also a question in my mind. The machine to blow. Then I wanted to see the simulation of this one. How the casting before the die is made, people make. Some companies make simulations. I asked them to give me the simulation part. This is the simulation one. This is a metal comes over here to the bottom, is about 12 inches and comes with this a bulb is there. See the white spot. Metal enters here, and the metal also enters here. Same time, for one cavity, there are 2 metal entries. And this black one is empty. Air is there. This air goes either here or either here. This was not correctly diagnosed by the simulation people. Air packet. It came to me. And I thought, where did you see this? See, but still it is getting filled here and filled here. And it causes turbulence also happening. tablet did not affect this. How to avoid air entry into the digestive system? A design practice is available and give you that option. This is the learning system I am trying to follow many years so that no air can go into. This is the rectangular type air design. If this down screw is the metal depressurizing area, this is the one goes up and down. This is the engage. This is the example. We found that this is very effective. This cross-section area AA, if it is 1, if you assume, this must be 4 times bigger in the cross-section B, and it should be at 2 times more area of the engage is 142 area. And this taper is 2 mm per side is very important, so that when you pour metal will not segregate on this. No air will go in this one. And we found in many of our applications, this was very nice and no air goes. So the drive was modified like this. It only one pouring system. Only one slight one. And it came down, and there is a resting point. And that goes here. Very quietly it goes here. This is for a different book. I'll tell you afterwards. The drive was modified and poured. This is the final gas. One goes down smoothly and this area is not very important. Board here to here is very important. And we also get a pass here, so we have to be this plan area. Castings were produced and machined. There is no blowhole at all in the 2020. See how it comes. Came from the solution came from the simulation. So, next.
Hello, sir. Siddharth here, sir. Thirugnanam, sir, can you hear me? Shekhar, are you? Am I audible? Shekhar. Shekhar, நான் பேசுறது கேக்குதா?
Yes, I can hear you, sir.
Thirugnanam, sir, can we open the floor for some questions?
Yes, it's audible. Now the slide is changing. Slide is changing.
Yes.
Okay. Anybody has any questions? Please, post it in the message, or feel free to unmute yourself and ask the question.
Oxide erosions when the fresh metal is in contact with the air, and if the molten metal is agitated too much while gas cleaning, oxides also charging more percentage of scrap also can cause oxidation. One of the method is don't agitate the metal too much. It is the basic from you. Second is you can go for filters and the runner side. This can avoid your oxidation. Mostly better not to charge more of scrap. Do not agitate metal. Don't lift the hurdle too much and then pour it into the air. This is my suggestion.
Thank you, sir.
Sir, can you show that case study of air blowhole?
Do we have any questions?
Yes, sir. Sir, can you just show that slide of air blowhole slide?
Okay. Thirugnanam, sir. We
Yes,
have a
sir.
question from Mr. Om Bandari.
Yeah.
Sir, can you please repeat your question a little louder?
Yes, sir. In case of that air blower slide that you had shown, that air blower is getting entrapped, sir. So the same case can be feasible for, let's say, the same kind of casting in terms of porosities. Are the porosity and can be entrapped in those kind of gating system? Sir, can you just show that slide? Then I can navigate and ask my question in detail.
This is one slide showing the
The types of
Shekhar,
air blowers.
Shekhar, can you help sir to show the slide?
Oh, okay. Okay, sir. Okay, sir. Okay, sir. Now sharing.
Yes, sir. Sir, just can you move on to the next slide?
Yeah. Which one you want to?
Yes, sir. This only. Can you move on to the next slide?
Yeah. This one. The next one.
Yes,
Then
sir.
move
The
on. You
next,
just tell me. Hold it.
where we can see the flow of metal. Yes, sir. In the stimulation one.
Yeah. Simulation. This is a simulation. Yeah. You tell me. It's louder. No problem.
Sir, so in the same type of
Hold
casting, sir,
it.
is there chances or the probability of porosity or entrapment in the casting instead of air blow
Yeah.
holes?
Actually, closely. Actually, when we pour this one, air is carried from this runner down and then getting it left. But it doesn't follow our rule. And there is this one size, this is one size, and something. It is branching up like this a river. So we found in the simulation there's a void. See this one also empty. No? This is empty. All the what is empty. Simulation is also empty. Empty is here.
Yes, sir. Yes.
There is a gravity. The whole place is atmosphere. So it's a question of air going along with the metal. Something wrong with the running system. See this one. This segregation is there. Void and all. See void. All the white are white. Yeah. What do you want to ask? Please louder.
No, sir. Sir, I was just confused. This kind of if the sprue bottom, even if the area would be reduced, it would be turned into a pressurized system. If we reduce the
Yeah.
pouring basin area, and even
Yeah.
so, the pocket of air which has been noticed that can be reduced drastically. Is this a possibility of doing instead of changing the whole gating system and the design? If we just reduce the sprue basin area and convert the gating system into a pressurized gating system, so this can be avoided, right?
No, I don't think so. You see, the point is now when you start pouring from this one, you getting at the bottom. Why it is flowing here also? There is a back pressure is created there. When the metal pours here, it is supposed to go straight there. If the metal flows freely, when this back pressure, it fills up and go material also flowing from this corner also. That should not be there. For filling any cavity, if it's a cavity, you should fill either from the top or either from bottom from one side, not both the sides. So there's a possibility of entering from here to here. And it will go here, it will go here also. Here it comes. If it goes in the front, it goes out. But it's getting trapped because when it comes from here to here, it gains speed also. That's a problem. So you should not have a runner of the fantasy. This one shape, here is one shape. There's no science in this. A lot of artistic nature is in it.
Yes, sir. Understood.
Okay. You have to follow some science, It's got no science. Any more questions, sir?
Any other questions? All right. I think it's time. So I'll conclude the session, and if you have any more questions, you can refer to the YouTube videos which will be posted in IIF chapter, or even I think Thirugnanam sir will always be welcome to answer any questions if anybody wants later also, as he's been a great teacher in our field for the past 50 years. So I'll take this opportunity to thank Mr. Thirugnanam sir for first giving his valuable time, because he was having schedule on Saturday, and he based on a request he has agreed to give his 2 hours to share his knowledge, his experience, which might be, as Hari sir said in the beginning, his experience alone is more than our age. So the amount of knowledge he shares, he's trying to share it to the young generation. So thank you, sir. Thank you so much for your time and patience. And I would like to thank all the members who have attended this useful session. And since he has taken us from the basics to individual case studies, I hope you guys all found it very useful in your work, and please follow IIF for all future updates on webinars, and we will keep you posted on our next session. Thank you, Thirugnanam sir. Thank you everyone. We will close the webinar for today. Thank you, sir.
Thank you, Siddharth. Thank you very much.